Okay, so good afternoon to all of you. Just a couple things before we start today. Today's obviously the last day of class. Just a reminder, not that you need the reminder, but your final exam is Monday at 11:30. So please remember that's a different time than the normal class time, and we'll be working right here in this classroom. I will talk more about the final exam near the end today. There will also be a question and answer period. I'll give you some review. We'll do teacher evaluations. But the first thing I want to do is just finish up the example problem that I started last time, and that was 996 from the 6th edition. Now, we had actually already seen the problem. It's still over here, but I'm going to get rid of that right away. We understand in this problem that this is a non-ideal, yet still simple air standard Brayton cycle. There's a compressor acting from 1 to 2. There's a heat input device, the combustion chamber acting from 2 to 3. We've got our turbine from 3 to 4. That's our work output device. And then we reject heat into the environment from 4 to 1, but we really do not need to quantify that. So this is the basic cycle, right? This is a non-ideal cycle, so I have shown the non-ideal compression from 1 to 2A. I've also shown the non-ideal expansion from 3 to 4A. But remember, we still have to use this tool. We still have to assume that it's a non-ideal, I'm sorry, we still have to assume that it's a ideal, that is isentropic process from 1 to 2S, and then use the isentropic efficiency to go from 2S to 2A. And we have to do the same thing for the turbine. We have to assume that it's ideal from 3 to 4S, isentropic if you will, and use the appropriate equations to get T4S, and then apply the isentropic efficiency to get the temperature at 4A. So that's the basic process. Once we have those actual temperatures, we'll just plug them into the appropriate equations. All these equations were presented last time, and we can get the results that we're looking for. So perhaps we could get rid of the problem statement over here now, and then we'll have better access to the board. All right, so first things first, we're almost always going to start a problem like this at state point 1, the input to the compressor. We know that for an isentropic process, the ratio of temperatures, T2S over T1, is equal to the pressure ratio to the K minus 1 over K power. This applies to our isentropic compressor. T2S is unknown, but T1 is known. The pressure ratio is known, right? We're given 2,000 kilopascals as our maximum and 100 kilopascals as our minimum. So this is our 2,000 to 100, in other words, 20 pressure ratio, and that has to be raised to the K minus 1 over K power. By the way, 0.4 over 1.4 is something like 0.2857 or something like that. So that might be something you want to remember. You can just go through the math. Anyway, this allows me to find the ideal temperature that would leave this compressor, if indeed it was an ideal device, of 706.1 Kelvin. Actually, I think we did this last time. Now we need to continue by using the compressor's isentropic efficiency. This is our relationship between the ideal work and the actual work. We know these are enthalpy changes, right? We know that the enthalpy change for an ideal gas with constant specific heats is Cp times temperature change, and the Cp's in the numerator and denominator would cancel, so this becomes nothing but a equation based on temperature change. So this would just be T2S minus T1 over T2 actual minus T1. So this is given to me as 0.8. T2S is known. T1 is known. We do need to make sure that we're using the appropriate units. Certainly we have to use Kelvin in the equation above. Here we can find the temperature difference either in Kelvin or Celsius. It'll be the same, but frankly, since all our numbers are in Kelvin, let's just leave them that way. And we end up with the temperature at 2A, that's our only unknown now, of 807.6 Kelvin. Right. So now we have that, and we're going to do exactly the same thing for the turbine. although we're going to use the turbine's efficiency instead of the compressors, but it's still the same basic process. So again, we assume that it's isentropic first. So T3 over T4S is equal to the pressure ratio to the K minus 1 over K. T3 is given. So converting it into Kelvin, it's 1,000 over T4S. And again, this equals the pressure ratio of 20 to 0.4 over 1.4. I believe I mentioned once upon a time that you should be using your calculator save memory button a lot. I mean, you've already done the RP to the K minus 1 over K when we did the compressor analysis above. So, I mean, you might as well just store that in memory and save yourself a minute when you're solving the problem. Nonetheless, we go through our mathematics and the T4S becomes 424.9 Kelvin. Now this would be the temperature if it were an ideal cycle, but it's not, right? Again, you're given isentropic efficiencies. So we use the turbine's isentropic efficiency, that's 0.9. And we note that this is the actual over the ideal work for the turbine. Again, this is the enthalpy change. The enthalpy change are CP times temperature changes. The CP's cancel. So this is going to be T3 minus T4 actual over T3 minus T4S ideal. So again, this is 0.9. T3 is known. T4 actual is the unknown. So, whoops, just plug in all the numbers that we have. And we solve for the actual temperature, leaving that turbine. And we get 482.4 Kelvin. So now we have all of our temperatures, and once we have all of our temperatures, there's really not a whole lot more to do but just apply those to the appropriate equations. If we're trying to find the thermodynamic efficiency, that's going to be a function of the net work. The net work, of course, is the turbine work minus the compressor work, and the efficiency is going to be a function of the heat input, which is, well, just CP times the temperature difference across that heat input device. So we know all that now. Right, so the thermal efficiency then is going to be net work over heat input, or if you will, the difference between the turbine and compressor work over the heat input. Now, I could either separately calculate each of these different work terms, or I could just plug in the equation, you know, CP delta T for each of these work or heat transfer terms, and then just let everything cancel out. You know, the CPs would all cancel out. I would only have a function of temperature, and that might be an easier way to do it. I'm not going to do it that way, simply because I think at this point you're still learning the material, and it's probably a little more useful to show you the equations, right? So the turbine work is going to be CP times the temperature change across the turbine. And in fact, here I need to be a little more careful to use the proper subscripts, right? The net work for the real cycle would be the actual work produced by the turbine minus the actual work required by the compressor. So it would make sense just to put the subscripts A, just to remind us that these are the real numbers, the actual numbers that we're using. So CP times T3 minus T4A is the actual work produced by the turbine. CP times T2A minus T1 is the actual work required by the compressor. And CP times T3 minus T2A, you know, the actual discharge of the compressor is 2A, so that's the actual input to the combustion chamber, right? So we have to use a 2A here. Now again, we have the value of CP, we have the value of all of these temperatures. Just plug in all the numbers. We get 520.2 kilojoules per kilogram for the work out. We get 510.1 kilojoules per kilogram for the work in to the compressor. And then the heat input is 193.4 kilojoules per kilogram. Once we have this information, now we can find the thermodynamic efficiency. So again, just plug in the numbers that are right here on the page and go through a little mathematics, and we end up with 0.0522 or 5.22%. Just a reminder, we cannot use the equation for the non-ideal cycle that applied to the ideal cycle, right? For the ideal cycle, you could use the equation 1 minus 1 over the pressure ratio to the K minus 1 over K. That's fine, but this is not an ideal cycle, right? This is the non-ideal Brayton cycle. So we need to use this version of the equation. Now again, we could have just plugged in the terms above and canceled everything out, just leaving us temperatures, and that would be an alternate way to do it. Lastly, the net work is just the difference between the turbine and the compressor work, so we can just take the difference between the two above, and we end up with 10.1 kilojoules per kilogram. So this is the net work per unit mass for this particular cycle. Now, one reason that I also solved it this way is because this problem may not be the end of a problem that would be similar to this one. For instance, what if I had asked you for the rate of heat input, or what if I asked you for the mass flow rate, or what if I asked you for the actual power, you know, the rate that work is being done? Then we need some other relationships, right? So for instance, one thing I could have done in this particular problem is given you the mass flow rate. So if m dot is given, then we could find such things, we could, for instance, find the net power, right? The net power is just the mass flow rate times the net work per unit mass. We could have also found, again, the heat input rate. That's just the mass flow rate times the heat input per unit mass. Some problems will be a little bit different than this. What if I gave you the rate of heat input or the power? Then you can use these same two equations above, but work backwards to find the mass flow rate, right? So if Q dot H or W dot net, or for that matter, W dot T or W dot C, if any of those are given, then you could find, the mass flow rate using, well, the equations similar to above. Right, so there's lots of different problems that would all be related, but you have to be really careful when you're solving them. The equations are always going to be the same. You have the full set of equations. None of this has changed really since we were talking about this material back in Chapter 7, but the problems are all a little bit different. So again, be careful, read them carefully, make sure you're using the equations properly. Are there any questions on this particular problem? Yes?
Why is it that the minimum temperature corresponds to 0.1 and the max corresponds to 0.3?
Well, there's many ways to answer that. I guess the easiest way is to just look at the TS diagram. We're always starting with atmospheric air. That's what's used in the compressor, and that's going to be the lowest point in the cycle. You know what we have right here in the environment. Once you compress it, you get to a higher temperature and pressure, and then once you add heat to that, at constant pressure, the temperature goes even higher. It's the output from that combustion chamber that's always going to represent the highest temperature in the process. Once you do work, you're going to end up at 0.4, but that's still going to be at a higher temperature than the surroundings. You're still going to have to reject heat into the environment to drop that temperature back down to 0.1. So, 0.1 is always the low point, always a low temperature in the cycle. 0.3 is always the high temperature in the cycle, and it's just based upon the way that these cycles work. So, is there a question here too?
Same question.
Okay. The author does do that a lot in the book, right? It often will give you a minimum and maximum temperature and just assume that you know what that means. Well, again, just look at the TS diagram. The TS diagrams are all going to look like this. They're not going to be significantly different. You're always going to have 3 as the high point temperature and 1 as a low point temperature. I mean, always. That doesn't mean that one can't conceive of other cycles that might work a little bit differently. But this is a Brayton cycle, okay? The Brayton cycle is the gas turbine, the jet engine cycle. It uses atmospheric air at 0.1. That has to be the low point. After combustion, that's what goes into the turbine. That 0.3 has to be the high point. I mean, that's the way this cycle works. Any other questions before we move on? Yeah.
So will we always be given like the minimum, maximum temperatures? We won't be given like TS, T2S and like T4S and like like you have to find T4.
I can't promise anything. All I can say for sure is that all the problems are going to be a little bit different. I think that one thing you might want to do as you're studying for your final is look at the problems that were given to you, whether it's examples or homework problems, and think about how you might want to solve them backwards. What if you started with the end result and worked backwards, just to give you a little bit of practice. Again, it's all the same equations, but I could certainly conceive of problems that would be sideways or backwards compared to what a typical problem would be. So yeah, I won't promise that I'm not going to do that. I mean, I think that there's plenty of problems that I could give you that you know, you'd be able to show me that you understand this material. What they actually are, well, you'll see on Monday, right? Yeah. And remember, too, that I did promise you a problem like this on the final exam. So this really brings together material from chapters 5, 6, and 7. If you can do a problem like this, that means you can solve a problem for a steady flow process. You can use thermodynamic efficiencies. You can use isentropic efficiencies, you can use ideal gas relationships. I mean, it kind of brings them all together. So that's why I rather like these Brayton cycle kind of problems. It just kind of shows a little bit of everything that we've been covering for the last month. Any other questions before we move on? All right, great. Well, this is the last example problem then that I'm going to do. And the other things that are left to do today are review and questions and answers, talk a little bit about the final. So I think what I want to do is let me start with the review. My intention is not to fill up the board here with equations. In fact, I really don't want to write down anything unless somebody has some specific questions. I'm just going to kind of talk through what we've been doing for the last 2.5 months, and then hopefully that all makes sense. If anything I say brings up a question, you can either interrupt me or just wait till the end and ask it later in the Q&A area or Q&A section. It's really up to you. So a little bit of a review then. So first of all, I tried to impress upon you the importance of thermodynamics for solving what will be some important types of problems in the future, right? The very first day, we actually talked about heat engines, we talked about refrigeration cycles. Even though you had no idea what those were or what kind of equipment one would use, I at least wanted to point you in the right direction. Then we really got into the material starting on the second day, so basic concepts, terminology, definitions. I mean, there's a whole new language of thermodynamics, right? This is where we talked about such things as state and property and equilibrium. We looked at various properties. We looked at extensive and intensive properties. We just tried to get a feel for the language, if you will. We learned about the word process. We learned about the prefix iso that would be used when something is constant. So there's a lot of terms that we looked at. The properties we looked at included such things as pressure, temperature, density, or specific volume, the inverse of density, and those are all measurable properties. But we also know that there's other properties that we cannot measure that are equally important and equally useful, such things as energy and enthalpy and entropy. So there's all sorts of properties. Now, we looked at the concept of energy. We I think, all generally understand that energy is really just a measure of our ability to do work or our ability to transfer heat. But we also realize that energy is in different forms. You could have an energy stored internal to your system. We call that internal energy. You could have energy based on the motion of the system, kinetic energy. You could have energy based upon its height in a gravitational field, the potential energy. We also note that energy can be transferred in a variety of ways, right? We can transfer energy as work. We can transfer energy as heat. But ultimately, the energy transfer has to equal the change in energy of our system, right? So that's where we eventually started to talk about the first law, but we're not really quite there yet. Once we understood the idea of these different properties, we started looking at pure substances. Hopefully it was clear that there's a lot of property data out there, but when you start dealing with mixtures, then it gets confused. and there isn't that much data out there for the wide variety of mixtures that might exist in this real world. So we're just looking at pure substances. Well, at least for now we are, right? In ME 302 we'll start looking at mixtures, but for now we were just looking at pure substances. It was hopefully made clear that if you know any two intensive properties, then that sets the thermodynamic state, and all other properties are known to us. So we can get those other properties either through, well, equations like the ideal gas equation of state, or through tables like the property tables for refrigerant 134A or water that are in your book, or even using graphs we can find relationships between properties, for instance the compressibility chart. But nonetheless, we were able to understand that property data exists in various forms. This is when we started talking about the different phases that existed, how we know that phases are just the way we observe these substances out there in the world, and that we can also have mixtures of phases, so we could have solids, liquids, or vapors. Those are the three phases. We could also have a mixture. For instance, we dealt a whole lot with liquid-vapor mixtures, right? It was hopefully made clear that it's mixtures of liquids and vapors that really represent the majority of the processes that we're going to deal with in this world. And in fact, as we started to go through problems, hopefully you saw that that was indeed true. You're often taking, let's say, liquid water and you're boiling it into a vapor. Sometimes you have a two-phase mixture during that process. You'll often have a refrigerant that's that is having heat added to it or removed from it, such you have, again, liquids or vapors. So the majority of the work that we're actually dealing with once we finished this discussion of pure substances was property data specifically deals with liquids and vapors. Now, for water or R134A, we've got really good tables, right? We have, well, mostly really good tables. We have superheat tables, so that's everything to the right of the saturated vapor. We've got mixture tables or saturation tables, so that's where we would use quality in order to find the thermodynamic properties for these two-phase mixtures. We also have compressed liquid tables, although we only have a water compressed liquid table. There's not one for R134A, and the property table for compressed liquid water starts at such a high pressure that it's practically useless. At least to us, it's practically useless. But that's okay, because one of the things I also mentioned at this point was that saturated liquids, let me reverse that, compressed liquids have approximately the same properties as a saturated liquid at the same temperature, right? And that would apply to enthalpy or internal energy or entropy or specific volume, any of the properties we'd be dealing with on a daily basis. For compressed liquids, we just take saturated liquid data at that temperature, and that's just fine. We also looked at ideal gases at this point, right? We looked at the ideal gas equation of state. It must have had at least 3 or 4 different versions, right? PV equals RT, PV equals MRT, PV equals NRT. Sometimes V is total volume, sometimes V is specific volume, sometimes V is the molar specific volume. Just make sure you follow the units through if you're confused at all about which form of that equation is correct or proper, and the units will always tell you whether you're doing it right. Nonetheless, we looked at ideal gases at that point. We also looked at real gases. We saw that there's a test one could make to determine whether a gas is an ideal gas. If it is an ideal gas, great. You can use the various ideal gas relationships that were yet to be covered. If it's not an ideal gas, that is, if it's a real gas, well, then we would have to use a compressibility chart. There are other equations of state for real gases that relate pressure, temperature, and volume, but we're not going to deal with any of those. The only one I ever had you look at was a compressibility chart. So all that was just in the first 3 weeks of class, just all the basics necessary to really begin looking at real problems. Finally then, we began looking at real problems. So this brings us to Chapter 4. At this point, the first law was developed for you for a closed system. In fact, Chapter 4 is closed systems, Chapter 5 is open systems, right? So we looked at the closed systems, and for closed systems, the first law is pretty straightforward. In fact, it's always straightforward. Heat transfer minus the work equals the change in internal energy plus the kinetic energy change plus potential energy change. I mean, that's the first law. And every problem we dealt with really for the next 2 weeks was just a variation on solutions to the first law. Lots of different types of problems, some constant volume problems, some constant pressure problems, like if we have a frictionless vertical piston cylinder device where the piston is free to move and maintain a constant pressure. So a lot of constant pressure problems. We had problems that were called polytropic, where P times V to the nth power is equal to some constant. So we saw how to calculate work specifically for that type of problem. And of course, there's no work for a constant volume problem because the work is integral to PDV, and if there's no volume change, there's no work. For a constant pressure problem, the work is just pressure times the change in volume. For a polytropic process, it depends on whether the exponent n is equal to 1 or not equal to 1, but some very specific equations for work. With regards to heat transfer, the heat transfer is something that would always be either given to you or would be the unknown we're solving for. In this class, we never dealt with heat transfer. We never dealt with the different modes of heat transfer, like conduction, convection, radiation, or how to calculate heat transfer or heat transfer rates. That will be left to your 415 class, which you'll get to eventually. Anyway, so we looked at all sorts of closed system problems. Not only did we look at problems associated with our pure substances like water or the refrigerant, but we also looked at ideal gas problems. And that's where we saw that the internal energy change is equal to CV times the temperature change. We also looked at solids and liquids at this point, and there it was shown that CP and CV were equal, and we just call that heat capacity. And as such, the internal energy change will actually equal the enthalpy change, which is equal to the heat capacity times the temperature change. So we looked at various problems associated with solids and liquids, again, as well as the ideal gases. And that took us right through about the middle of this course. Then we started to look at the open system problems. So what I did, at least in this class, was I derived the first law for an open system from the first law for a closed system. And then we started to look at some of the special cases. We realized that the most common is the steady flow type of process. So the first law was then further developed specifically for these different types of processes for steady flow processes, right? So we have heat exchangers, mixing chambers, throttles, pumps, turbines, compressors, nozzles, diffusers, throttles. I mean, I think that's the list of these steady flow devices. Once the equation was developed for the general first law for the steady flow process, then we looked at the even more specific special case of the single stream steady flow process, like a turbine, pump, compressor, nozzle, diffuser, throttle. And most of the problems we looked at actually fit into that category, right? Single stream steady flow processes. So we looked at that. We also looked at multiple stream steady flow processes, again, like the heat exchanger, like the mixing chamber. For all of these, the basic equation is pretty much the same, right? Basically, the heat transfer minus the work equals the sum over all inlet streams of the mass flow rate times the enthalpy at the inlet, well, plus kinetic and potential energy, and then minus the sum over all exit streams of the mass flow rate times the enthalpy and kinetic and potential energies for each exit stream. I mean, that was a general equation. Fortunately, we never looked at anything that had more than just two inputs or two outputs, like a heat exchanger, right? So it became a much simpler equation. And then after we looked at that, I might note that we looked at some problems that involved water or the refrigerant. We looked at other problems that dealt with just ideal gases, where we would have to use for the enthalpy change, Cp delta T, just like for the internal energy change. In the previous closed system problems, we used Cv times delta T to give us our change in internal energy. Let me note again that for an ideal gas, the internal energy change is Cv times delta T. And for an ideal gas, the enthalpy change is Cp times delta T. Students ask me all the time, how do we know whether to use Cp or Cv? That shouldn't even be asked, really. If you're finding internal energy, it's always Cv. If you're finding enthalpy, it's always Cp. Just go back to the definition of internal energy, or I'm sorry, go back to the definition of specific heat at constant pressure or constant volume. When we first started looking at ideal gases and look at that derivation, U and Cv are related. Cv and U are part of the same definition, right? H and Cp are related. So if you need internal energy, you find Cv. If you need enthalpy, you find Cp data, and you work on it from there. You have a question?
Yeah. So to sum that up, basically like in the chapter 4 where our closed system was, Q minus W equals m dot delta U. if
Okay.
that's an ideal gas, we turn delta U into Cp,
Mhm.
delta T, and then if it's
Right.
an open system where it's delta H, we can just turn that into Cp delta T.
Right, but make sure that it's an ideal gas.
Right.
And I might note that if you have something like water vapor, use table A6. You always want to use your superheat tables. If you have refrigerant vapor, then use table A13. You may have an ideal gas for superheated water vapor or superheated refrigerant, but why use that assumption? I mean, when you're using ideal gas, I mean, the word ideal means that you're essentially assuming something that can't really be, right? Is there really an ideal gas? No, nothing is really ideal in this world of ours. So it's always better to use the actual thermodynamic property data when it's available to you, and we have good water and refrigerant data, so always use it. Anyway, any other questions before I continue? All right. So when we're looking at open systems, again, we looked at these different types of processes, both for ideal gases and for the different pure substances. We also looked at the uniform flow problems. These were sometimes called charging or discharging problems. So the first law was a little bit different, but mainly because the internal energy is changing within our system, right? If we're talking about a steady flow process, there's no change within the system. The thermodynamic state is always going to be the same. You'll have something different going in versus going out, but within the system, there's no changes. However, for the uniform flow problems, charging, discharging problems, there definitely is a change within our system, right? We're emptying or filling a vessel. As such, the properties are going to change within that vessel. So we definitely are going to have a term that deals with the initial internal energy, an M1U1 term, and there'll be a term dealing with the final internal energy, the M2U2 term. And keep in mind as well that the mass is going to be different in these charging and discharging problems between the beginning and the end of the process, right? For a charging problem, the mass is going to rise. For a discharge problem, the mass is going to fall. So we definitely have to keep track of the initial and final mass, M1 and M2, as well as the inlet or the exit mass, ME or MI, and those then get factored into our first law equation. So that took us through Chapter 5. Now we get into Chapter 6, and this is where we were first introduced to the concept of thermodynamic efficiency, and we specifically looked at the refrigeration cycle and the heat engine cycle. The heat engine is a device where we turn heat into work. Of course, the second law tells us that the only way to do that is to reject heat at the same time. We also looked at the refrigeration cycles, and the refrigeration cycle is where we're transferring heat from a low temperature source to a higher temperature heat sink, and of course that can't happen all by itself. The only way that can happen is if we provide some sort of work input. We looked at both the heat pump as well as the refrigerator, freezer, air conditioner type of refrigeration cycle. They're the same cycle. I mean, it's just a refrigeration cycle. Heat added at low temperature, work in, heat rejected at high temperature. The cycles are the same, but what is of use to us is different, right? For a heat pump, we're interested in the heat that is rejected from the cycle into the space we're trying to keep warm. For a refrigerator, freezer, or air conditioner, we're concerned with heat that's being taken out of the space that we're trying to keep cold, like the food in our refrigerator or the cold air inside of our house during a hot day when we're air conditioning that house. So as such, you would have different definitions of coefficient of performance for those two different types of refrigeration cycles. There's only one type of heat engine, so we only have one thermodynamic efficiency equation. But again, the coefficient of performance is our performance characteristic for the refrigeration cycle. QL is used for refrigerator, freezers, or air conditioners, right? And QH is used for heat pumps within those equations. We also at that point looked at the Carnot cycle just to give ourselves a feel for what would be the best possible cycle that could operate between any two temperature limits. We saw that the thermodynamic efficiency or the coefficient of performance for the Carnot cycle is only a function of temperature. So that makes it nice and easy. And then we can actually compare our real cycle to our ideal, our Carnot cycle, to determine whether a process that we're analyzing, and this would be some sort of a cyclical process, right? A refrigerator, freezer, air conditioner, heat engine of some sort. We could compare the actual thermodynamic efficiency or coefficient of performance to the Carnot cycle value and see whether that process is real or ideal or simply impossible. That's when we first started looking at the second law of thermodynamics. Essentially, that statement is a statement of the second law of thermodynamics. Nothing can have a higher thermal efficiency than the Carnot cycle operating between two temperature limits. Nothing can have a higher coefficient of performance than a refrigeration cycle operating under the Carnot cycle between those same two temperature limits. So that was our introduction to the second law of thermodynamics. However, that really wasn't sufficient, right? I mean, we're not only interested in cycles, we're interested in individual processes. So this is where the whole concept of entropy was introduced to you. I actually derived for you the existence of the property entropy. And the way we interpret entropy is as a measure of randomness or disorder. But that interpretation is really meaningless. What we want is to use entropy to see if certain processes can or cannot occur. So we looked at entropy changes, and what we found is that the total entropy change for a system that we can also call the entropy generation has to be positive. If that total entropy change is positive, then the process is possible. It satisfies the second law. If the total entropy change is negative, then that's impossible. It does not. It violates the second law. And the way to do that was to look at the entropy change of the system plus the entropy change of the surroundings. Now, the entropy change of the system was simple, right? Entropy, being a property, has tabulated values that are inside the property tables in your book. So if you want to find the entropy change of the system, you just look up the data. The entropy change of the surroundings is even easier because we recognize that the surroundings are so huge compared to the system that's being analyzed that it's essentially an ideal isothermal process, and as such, the entropy change is just Q over T. So we just had to quantify the heat transfer so that we could then find the Q over T for the surroundings, and that will give you, when added to the entropy change of the system, the total entropy change for that particular process. So that's what we dealt with regards to entropy. Of course, we also looked at pure substances as well as ideal gases to find ways to calculate these problems or go through these problems. I think I made it clear that these second law problems were actually just first law problems in disguise, right? We still have to find the heat transfer so that we can find the entropy change of the surroundings. And how do you find the heat transfer but by solving the first law of thermodynamics? So all these second law problems, these entropy problems, really are just first law problems with a little bit added on to the end to determine whether the entropy change, the total entropy change, the entropy generation, if you will, is indeed positive. Now, we also looked at isentropic processes at this point. You know, we realized that there might be a process with no entropy change, and that isentropic process would represent the ideal process, the reversible process that's taking place. So we looked at ideal steady flow devices. We looked at ideal turbines, we looked at ideal pumps, we looked at ideal compressors. And then the concept of isentropic efficiency was introduced to you. We realized that the way we would actually determine the thermodynamic state of the substance leaving one of these steady flow devices, a pump, turbine, or compressor, is to first assume that it is isentropic. That isentropic process will then give you the value, either the enthalpy or the temperature leaving that particular device, but I put the subscript S on there because that would be the ideal properties leaving that device. And then you'd be given an isentropic efficiency for that pump, turbine, or compressor, and then you would apply that, and that would convert your ideal data into your actual data. I mean, really what you're finding here is a relationship between the ideal work and the actual work, right? The ideal work is going to be a function of the enthalpy change for a compressor. It'd be like, say, H2S minus H1. The actual work is also a function of the enthalpy change, but it's going to be H2 actual minus H1, and then the ratio of the two is your isentropic efficiency. So once we got into isentropic efficiencies, we realized that the way to solve those problems is to assume that it's an ideal process first, find the ideal discharge state, 0.2s, 0.4s, whatever it happens to be, and then apply the isentropic efficiency to get the actual discharge state. And then at that actual discharge state, well, then you can find your work, you can find your heat transfer, you can find maybe, well, other information as is necessary or important. So that was pretty much the end of Chapter 7. One thing I will note is that I also covered that section on reversible steady flow work, where it turns out for a liquid undergoing an isentropic process, the enthalpy change, which is your ideal work, is also equal to the specific volume times the pressure change. Now that only applies to a liquid and only for an isentropic process, and even though I gave you a homework problem or two, that's not really something that's going to be emphasized. That will be part of ME302 when we start analyzing pumps as part of a cycle that's actually very similar to the Brayton cycle that we've been dealing with over the last week. You can have a cycle like the Brayton cycle that uses water or steam, and we call it a Rankine cycle, and that's going to be something that will be covered in ME302. But a Rankine cycle requires a pump, and that's where you're going to have to use that specific volume times delta P relationship to get the work. Lastly then, we dealt with gas power cycles. The only gas power cycle that we dealt with was the Brayton cycle. We looked at just the simple Brayton cycle. Please note once again that I did not assign many sections from Chapter 9, only the first few that deal with the general gas power cycles and talks all about the whole idea of being an air standard cycle. And then Section 9.8, which is your simple Brayton cycle. There's a lot of other information about other types of cycles that you're totally not responsible for. So just deal with the Brayton cycle. And keep in mind that the Brayton cycle deals with the same things that we've already been learning about all quarter long, right? Well, not all quarter long, but certainly since Chapter 5. And that was something that I just explained at some length earlier in today's lecture, so I don't think I'm going to go through that again. But that then is just a summary of the course. And by the way, I'm just going off of my syllabus here. I don't have pages, spread out in front of me that tell me what I need to cover today. This is just basically my recollection of what we were covering in this class. So hopefully you recall the same thing, and you can show me so on your final exam, and hopefully I'll pass everybody, and that will make me very happy. So we'll see if that happens. Has it happened before? I don't know. I taught this course for a long time, and no, never ever. But you guys are lucky. You had at least one student that stopped showing up a few weeks ago, so maybe that'll be the one and only F in the class. Okay, so we'll see. So at this point, are there any questions then on any of this material, homework problems, basic problems? I haven't yet talked about the final, but I'll get to that shortly.
I wasn't material. I was wondering, we can bring 2 note cards, right?
No, I think I just said 1 note card for this, yeah. Should I talk about the final now? Did you have a question on material?
For polytropic, how do you know it's polytropic?
Okay, good question. I like to think of polytropic processes as kind of a catch-all, okay? Keep in mind that when you're dealing with a polytropic process, it really just tells you that the relationship between pressure and volume is a continuous polynomial function. We go from point 1 to 2 following any of a number of lines, and as long as it's continuous in this fashion, then there will be some exponent n and some constant c that would give you the exact equation, or at least pretty close to the exact equation, for the actual process that takes place. With that in mind, you would have to be told that it's a polytropic process. You couldn't just guess that. There's only one situation where you would know it's polytropic without being told, and that's if you have an ideal gas undergoing an isothermal, that is constant temperature process. In that case, mass, R, and T are all constant, so PV equals MRT. PV equals a constant, and that satisfies this equation. PV to the first power equals a constant. So for an ideal gas undergoing an undergoing an isothermal process, yes, it's polytropic with n equal to 1, but otherwise you would always have to be given the value of n. In fact, we don't even need c. When we do the integral of PDV and calculate the work, it turns out that constant's going to cancel out anyway. So the only thing we really need are the values of p and v at the initial and final points, 1 and 2, as well as the numerical value of n. Sometimes n is given, sometimes it's not. Sometimes you'll be given pressure and volume data, and then you just have to use p1 v1 to the n equals p2 v2 to the n and calculate n that way. But you still need n so that you can calculate the work, and then that work will be part of your first law, and then presumably you'll use the first law to find some final state, some heat transfer, whatever. Any other questions? Yeah.
If it's polytropic, are you always allowed to use P1 V1 to the n equals P2 V2 to the n?
Yep. If P times V to the n is a constant, then that means that that equation applies at every single point. So you can use it at point 1, you can use it at point 2, you can use it at any of the intermediate points if you knew what they were. But yeah, I would apply it at any state point. Mhm. Yeah.
So I remember thing we do one of the thermal problems, and there's heat fusion. Do we ever use heat fusion?
When we talk about fusion, we're talking about the phase change between a solid and a liquid. And I haven't really gone into any problems like that. All the phase change problems we've looked at involve vaporization, so we can say heat of vaporization. In fact, HFG, you know, the difference between HG and HF is often called the heat of vaporization. And if we had a fusion process, you know, for melting ice or for solidifying water into ice, you know, that heat of fusion is just, well, the difference between the solid and the liquid phase. But we haven't looked at any problems like that, and I can't imagine I'm going to give you something like that. No. Yeah.
Real quick, can you go over the sign convention for work and Q-term in the first one?
Okay, so the first law is a general equation, and we have to respect the various signs that are within that equation. But there's also a sign convention that has to be covered. Now, if you look at this material in your textbook, the author likes to talk about heat in, heat out, work in, work out. That's fine, but I prefer just to think about it as heat or work with the appropriate sign. If heat is added, heat into the system is positive, and if heat is lost, heat rejected from the system is negative. Work is actually the opposite of that. If work is being done by the system, you know, if the system is actually pushing onto its surroundings and doing work, in other words, work output, then that's going to be considered positive. And work input, you know, if we're pushing on the system, or maybe we have something like a compressor, right, where work is being done to the fluid moving through that compressor, then that would be considered negative. So heat in is positive, work out is positive. Heat out is negative, work in is negative. Yeah. Okay. And then keep in mind, too, that when we looked at the thermodynamic efficiency equation, or coefficient of performance equation, in that case only, the heat transfer and work terms are always taken as absolute values, and then the sign was actually placed into the equation itself. So for instance, if we have a thermal efficiency as the difference between the turbine work and compressor work over the heat input, well, we know that compressor work is negative because it's work required by the system. I don't show it as W turbine plus W compressor with W compressor as a negative value. I just show it as W turbine minus work compressor with work compressor as the absolute value of the work that is required. So yeah, just make sure that within your thermodynamic efficiency or COP equations, you use magnitudes or absolute values.
And if there's an external work from electricity or from
Like a mixing device or something like that.
Those would be negative, right?
Well, yeah, because they would involve work input. Yeah, so any work input from a mixer, any work input from electric resistance heating, or an electric resistor, yeah, those are always definitely negatives because they're inputs. Mm-hmm. Any other questions? Yeah.
Some of our example problems, we assume that the gas is an ideal gas. Under what circumstances can we make that assumption?
If you have, well, let me just put it this way. The only time we even looked at the difference between ideal gas and a real gas is if we were dealing with a specific volume and, you know, using the compressibility chart. But the only method that we ever used to solve first law problems for gases was to assume that it was an ideal gas. When you assume it's an ideal gas, then you can use the fact that the internal energy is the integral of CV dt, and that the enthalpy, well, change in enthalpy really, is the integral of Cp dt. So if you're solving a first law problem, which then by extension, if you're solving a second law problem, then you are always just going to assume it's an ideal gas because that's the only method of solution that we have. So you never even have to take it beyond that. If you're going to assume it's an ideal gas, just assume it and use ideal gas relationships. You don't have to check whether it's an ideal gas or not because it's the only method we have, and that should be sufficient. Okay. Okay. Yeah.
So if it's not ideal, then you can use this one?
Well, if it's not an ideal gas, we just haven't looked at the methodologies to find the enthalpy data or the internal energy data. I mean, if we had property tables similar to, say, our well, our water tables or refrigerant 134A tables, where we can just look up property data like H, U, etc., then we would use those. But the fact is that for gases, we just don't. Now, there is a set of tables, I think it's A17 to about A27 or so in your book, and those are gas tables, but those are still ideal gas tables, okay? Those are ideal gas tables with variable specific heat, and that's something that we just have not talked about in this class. So I know that the author describes using that method, using the data from table A17 for various problems in chapters 4 and 5, even in 7, but that's not something we've ever done. So yeah, we're always just going to assume ideal gas and use the ideal gas relationships. Okay.
And if we weren't given an ideal gas on the final, we just use the compressibility chart to find Z and N.
Well, right, but I mean, you know, on that first test, I just wanted to make sure people were paying attention and understood there was a difference between a real gas and an ideal gas. At this point, we're only dealing with ideal gases, so I can't imagine that I'm going to give you a problem that just says, is this gas a real gas or an ideal gas? I mean, those are real simple problems, and the problems you'll see on the final are really more similar to the kind of problems that we've seen, well, over these last 7 or so weeks. So let me talk a little bit about the final, then I need to leave at least 5 minutes or 10 at the end to do evaluations. So, all right, so first of all, there's going to be just 4 problems on the final, but some of them might be multiple part. The final will cover material from the entire class, but there will be emphasis on material that you have not yet covered. And I did already tell you that you will definitely get a Brayton cycle problem, and it might be a non-ideal Brayton cycle problem. So you definitely want to make sure that you understand all this material. You will be allowed to use a note card, just one note card, 3x5, written on both sides with equations only. You're really not allowed to write sample problems or step-by-step methods of solution or anything like that. I will note that it might be rather difficult to put everything you've learned on one little note card, so don't fill it up with things that you already know about. Just fill it up with things that you don't want to memorize. You know, there are certain equations that are too long to memorize, and I think you should be kind of careful with your 3x5 card. You'll have the full 2 hours. I will give you a property table handout like your midterms. If you have your own property table handout, you can certainly bring that with you. You know, mine is on both sides, kind of 2 pages per sheet. You may want to print one off in color, or just 1 page per sheet, single-sided, if it'll make it easier for you to read or go through it. But that's up to you, and all that is available online, you know, through Blackboard. All lectures through Wednesday's lecture have already been put onto the Blackboard system, so if you need to review anything and you want to go through those lectures, they're available through Blackboard, and they're all just YouTube videos, so those are available to you. Are there any questions? Anything you didn't mention?
Today's will be by sometime this weekend uploaded too.
Today's, well, lately I've been getting these things within like an hour or so of class, so you know, hopefully, I mean, I can't guarantee it, but you know, hopefully they'll be up before the end of the day.
Okay.
So I would plan on it.
Can I draw the Brayton cycle on my note card?
You know, I don't mind if you have a sketch or 2 for yourself. Yeah, so if you want to show a Brayton cycle, yeah, you can do that kind of a sketch. If you want to show some cycles, you know, that's not a big deal. I'd let you do that. You know, PV diagram, TS diagram. Why don't we just say, yeah, if you want to have diagrams as well as equations, then that's okay with me. Okay. Again, the final is at 11:30, not 1 o'clock, right? So make sure you come here at the right time, and it's on Monday. My finals week office hours were different. I put those on the board here last time. If anybody didn't get those, come see me afterwards or talk to one of your classmates. But I'll be in my office today until 3:30. I'll be there again at 8:30 until 9. But I do have a final right before yours Monday morning, so I'll only be there from 8:30 to 9 Monday. Okay, so now it's time for teacher evaluations.